You have likely encountered macros in constants, header cards, or third-party libraries. While often discouraged in favor of safer modern alternatives, the preprocessor remains essential in professional C++. Mastery requires understanding how macros work, when to use them, and crucially, when to replace them. To understand macros, we must look at the build pipeline. Compiling is not a single step. It begins with the preprocessor. Think of the preprocessor as an automated text editor that runs before the compiler. It is unaware of C++ concepts like variables, types, or scope. It operates solely on text tokens. Macros are instructions for this tool to copy, paste, and modify your source code. The output of this text manipulation is called a translation unit. Let's look at this basic example to visualize this. When you run your build command, the preprocessor scans this file looking for lines starting with a hash symbol. It sees the defined directive for myConstant. It stores that definition in memory. Then it scans the rest of the file. Every time it encounters the text myConstant, it strictly replaces it with the text 100. If you run the compiler with the /p flag or configure Visual Studio to preprocess to a file, the compiling process stops immediately after the preprocessor finishes. The code the actual compiler receives looks like this after the preprocessing. Notice that the defined line is gone. It has been consumed. The variable x is now being assigned the literal number 100. This distinction is vital because if you have a syntax error in your macro, the compiler won't report the error on the line where you defined the macro. It will report it on the line where the macro was expanded. This is why macro debugging can be so frustrating. We classify macros into two main categories, object-like macros and function-like macros. We just looked at an object-like macro. It looks like a data object. It is an identifier that gets replaced by a code fragment. For decades, this was the standard way to define constants in C and early C++. You would see code bases defining mathematical constants, buffer sizes, and configuration flags using this method. By convention, we use all capital letters for macro names. This is not a syntax rule. The computer does not care. We just do this as a warning sign for humans. When a programmer sees a word in all caps, it signals that this is not a variable. It does not obey namespace rules and it is a clear text replacement. However, there is a massive downside to using macros for constants. Because the preprocessor strips the name out before the compiler sees it, you lose type safety and you lose symbol information. If you are stepping through this code in the debugger, you cannot hover over myConstant to see its value, because myConstant no longer exists in the binary. It is just the number 100. This is why in modern C++ we almost strictly prefer using the constexpr keyword for constants. With the constexpr version, maxuser is a real symbol. It has a type of integer. It lives inside the namespace. The debugger can see it. For simple constants, you should practically never use macros nowadays. However, object-like macros are still the standard for feature flags and include guards, which we will discuss later. Now we move to the more complex category, function-like macros. These look like function calls, they act like function calls, but they are definitely not function calls. A function-like macro takes arguments. The preprocessor replaces the macro name and uses those arguments to construct the replacement text. This allows for generic programming that works on any data type, simply because the preprocessor ignores types entirely. Let's look at a classic example, a macro to square a number. When the preprocessor runs, it finds square parentheses 5 and simply swaps x for 5. The code becomes int result equals 5 times 5. This works as expected and returns 25. However, this implementation has a flaw involving operator precedence. Remember that macros are just text copy-paste operations, not mathematical functions. If we pass an expression like 5 plus 1 into our macro, the preprocessor pastes it exactly as written. We expect 5 plus 1 squared, which is 36. But look at what is actually generated. The preprocessor expands square 5 plus 1 into 5 plus 1 times 5 plus 1. Because multiplication happens before addition, the compiler calculates 1 times 5 first, resulting in 5 plus 1, which equals 11. To fix this, we need parentheses, so we must explicitly enforce the grouping of the arguments. We wrap the usage of the argument x in parentheses inside the macro definition. Now, if we run the expansion again, the parentheses force the addition to happen before the multiplication. We get 36. We solved it, right? Not quite. Imagine we use our macro in a division operation. We want to calculate 100 divided by the square of 5. Mathematical precedence goes left to right for multiplication and division. The compiler calculates 100 divided by 5, which is 20. Then it multiplies that by 5. The result is 100. This is really bad because we expected 4. To fix this, we need to treat the entire result of the macro as a single atomic unit. We must wrap the entire macro definition in parentheses. Now the expansion looks like this. The outer parentheses force the multiplication to finish before the division occurs. This leads us to the golden rule of C++ macros. Parenthesize every argument and parenthesize the entire result. If you fail to do this, your code may break in the most confusing way possible. Whenever you combine your macro with another operator. Even with all our parentheses, this macro has a fatal flaw that cannot be fixed with syntax. This is the problem of double evaluation. Because a macro is a text replacement, the argument you pass in is pasted into the code as many times as it appears in the definition. In our square macro, the input x appears twice. If you pass a pure value like 5, this is fine. But what if you pass an expression that modifies a variable? A common pattern in C++ is the post-increment operator, the ++. Let's see what happens if we try to square a variable while incrementing it. A normal function would take the value 5, square it to 25, and then increment a to 6. But let's look at the expansion. We have now executed the increment operator twice on the same variable within a single statement. This is actually undefined behavior in C++ depending on the version. But practically speaking, a will likely end up being incremented twice. We might get 5 times 6 or 5 times 5, but a will end up as 7, not 6. This is the hard limit of C++ macros. You cannot prevent double evaluation if your macro uses the argument more than once. This is the primary reason why for simple math like min, max or square, you should always use inline functions or templates instead. An inline function evaluates the argument once, binds it to a parameter, and then executes the logic. However, recognizing this limitation helps us understand when to use macros. Macros are not for math. Macros are for code manipulation where we specifically want to operate on the text structure of the code, or where we need to control the compilation environment. Okay, we just spent some time bashing macros for being bad at math. But now we are going to look at what macros are good at, manipulating source code itself. There are things you simply cannot do with standard C++ functions because functions operate on values at runtime, while macros operate on tokens at compile time. Next up is the Stringizing operator, written as a single hashtag. This operation converts a macro argument directly into a string literal. Effectively, the preprocessor takes the text you pass to the macro and wraps it in double quotes. But why is this useful? Imagine you are writing a debugging tool. You want to print the value of a variable, but you also want to print the name of the variable, so you know what you are looking at. In standard C++, a function receives the value 5, but it has no idea that the variable was named userCount, for example. With the Stringizing operator, we can capture that name. Take a look at this code. When the preprocessor hits print var, it sees the hashtag x instruction. It takes the token userCount and turns it into the string userCount. Then the second usage of X is just a normal variable expansion. The expanded code looks like this. This output is incredibly valuable for logging systems. You can serialize data structures to JSON using the variable name as the key or build assertion libraries that tell you exactly which expression failed rather than just crashing. If the stringizing operator is about turning code into text, then the token pasting operator is about generating new code. It is denoted by two hash symbols. This operator concatenates two tokens together to form a single new token. This happens before the compiler tries to understand what the code means. This allows you to generate variable names or function names programmatically. This is often used to reduce boilerplate code. Let's say you are writing a library that handles different command types, and for every command, you need a specific handler function with a given prefix followed by the command name. Writing these out manually is tedious and error-prone. We can automate this pattern like this. The preprocessor sees handle underscore on the left and command name on the right. The double hash glues them together. To the compiler, it looks like you manually typed out valid function names. This technique is often used in game engines or UI frameworks where you have hundreds of events or properties that all follow a strict naming convention. It guarantees that your naming scheme is consistent because the macro enforces it. Now that we can manipulate names and strings, we need context. C++ compilers come with a set of predefined macros. They are populated automatically by the compiler environment. These are not macros you have to define. They are macros that are always there, ready to give you information about the code that is being compiled. The most common ones are the following: line, file, date, and time. There is also one for functions, which holds the current function name. These are essential for building a robust logging system. If you print the file name and line number, you know exactly where to fix the bug. Let's combine everything we have learned. The stringizing operator, the do-while loop for safety, which we will cover more in depth later, and predefined macros. Let's build a professional logging macro. When process data runs, the preprocessor replaces line with the actual line number of the source file, and file with the string path of the file. The output acts as a stack trace fragment. This is dynamic content that changes based on where the macro is placed in your source code. You cannot achieve this with a standard function. If you wrote a void log error function and called it, line would report the line number inside the log function, not the line number where the error occurred. This is a use case where macros are still strictly superior to modern C++ functions. Finally, we have conditional compilation. This is the ability to include or exclude chunks of code based on logic. We control this with directives like ifdef, ifndef, as, and endif. The most universal use case is the include guard. When you create a header file, say player.age, you might include it in game.cpp and also in enemy.h. If game.cpp includes both, the preprocessor will paste the contents of player.h twice. This causes a multiple definition error, because the compiler sees the player class defined two times. To stop this, we wrap the entire header file in a guard. The first time the preprocessor sees this, player_h is not defined. It then enters the block, defines player_h and includes the class. The second time it sees this file in the same translation unit, player_h is already defined. The preprocessor skips everything until #endif. The compiler effectively sees an empty file the second time. While modern compilers support Pragma once, which handles this in one line, understanding the ifndef pattern is critical because it is the foundation of cross-platform development. You will often see code like this in professional libraries. This is the standard approach for cross-platform compatibility. The preprocessor checks the build target before compilation begins. If you are compiling on Windows, it keeps the Windows block and physically removes the Linux block from the source. the compiler only sees the code relevant to the current system, preventing errors from unsupported functions. We have covered macros that take a fixed number of arguments, like our square macro example, but sometimes you need a macro that can accept any number of arguments. This is called a variadic macro. If you've ever used printf in C or C++, you know it takes a format string followed by an unlimited list of variables. If we want to write a macro wrapper around printf, perhaps to add the new line automatically or include a timestamp, we need a way to pass that variable list through the macro. To do this, we use the ellipses or three dots in the parameter list and the special identifier va_args in the replacement text. When the preprocessor sees the three dots, it gathers all the remaining arguments into a single bundle. When it sees va_args, it dumps that bundle into the code. However, there is a subtle bug in the code I just showed you. It works fine if you have arguments, but what if you just want to print a simple string with no extra variables? Notice the trailing comma at the end. We passed nothing into the three dots, so va_args is empty, but the comma we typed before va_args is still there. This syntax error will break the build. To fix this, non-standard compilers introduce the specific trick. Placing the token paste operator, the double hash, right before va_args, then it acts like a smart delete key. If your argument list is empty, the preprocessor automatically removes the trailing comma, keeping your syntax valid. Now, if va_args is empty, the preprocessor removes the comma and the code compiles perfectly. Now, we must address a structural problem. As your macros get more complex, they often span multiple lines. For multi-line macros, we need to group the statements together so they execute as a unit. The most obvious way to do this is by wrapping the lines in standard curly braces. This looks like a valid scope, but it fails in one specific, very common scenario, the if-else statement. In C++, we end statements with semicolons, so we put a semicolon after check and alert. Let's see how this expands. The trailing semicolon after the closing brace is taken by the compiler as an empty statement. The if statement finishes right there. The else keyword is now orphaned. It has no matching if. So the compiler will throw a syntax error. To make a multi-line macro act like a single function call that swallows the semicolon correctly, we use the do-while zero loop. The do-while loop always executes at least once. Since the condition is 0, which is false, it executes exactly once. Crucially, a do-while loop requires a semicolon at the end of the while clause. Now our expansion looks like this. It's valid syntax. The loop is optimized away by the compiler, generating zero overhead. But it makes the macro robust enough to be used anywhere a normal function call can be used. If you are writing a macro with more than one statement, you must use this idiom. We have arrived at the final boss of C++ macros, the X macro. This is a technique used to maintain data that needs to be represented in multiple different ways, typically as an enum and as a string array. Imagine you have a list of colors. You need a color enum so you can use them in switch statements efficiently. But you also need a function called string_from_color so you can print them to the UI. In normal C++, you have to maintain two lists. If you add yellow to the enum but forget to add it to the string array, your program will crash or print garbage. This violates the dry principle. Don't repeat yourself. X macros solve this by defining the data once in a macro list, and then using the preprocessor to generate both the enum and the string array from that single source. First, let's define the data table. We can call this the list of colors. It consists of calls to a macro named X, hence the name, passing in the data. Step 2. Generate the enum. We define a local macro X that simply takes an item name and outputs it with a comma. When we place list of colors inside the enum definition, the preprocessor iterates through the list, applying that rule to every item. This automatically generates the valid enum syntax. We then undefine X immediately to keep the global namespace clean. Step 3. Generate the strings. We define X again, but this time we use the stringizing operator. This turns the token name into a string literal. Now the preprocessor generates the color strings: red, green, blue, yellow. And by simply changing the definition of X, we produce a completely different code from the same source list. So if we ever need to add a new color, like purple, we add X parentheses purple to list of colors. Both the enum and the string array are updated automatically. It is now impossible for the data to be out of sync. This technique is incredibly powerful for things like configuration settings. It is widely considered the one acceptable use of complex macros in modern C++, because achieving this with templates or standard C++ is rather difficult and verbose without external code generation tools. Okay, we have learned how to manipulate the preprocessor. However, the trajectory of modern C++, specifically from C++11 through C++20, well, it has been focused on making the preprocessor unnecessary. The general rule in professional software development today is simple. If you can do it without a macro, you should do it without a macro. Let's examine the specific replacements available to you, starting with object-like macros. As we discussed earlier, using define for constants is poor practice, because it disregards scope. Consider this scenario involving a common name like size. Because the header file defined size as 100, the preprocessor blindly replaces the variable named size in your function with the number 100. The compiler sees int 100 equals to 50, which is invalid syntax. If this macro came from another header, then it is called namespace pollution. The macro leaks out of the library and breaks unrelated code. For a modern solution, use constexpr. By using constexpr, the value is typed. It is scoped to the namespace and it does not interfere with the local variable named size unless you explicitly access it via its namespace. For function-like macros, the standard replacement is the template function. We previously saw how the square macro failed when passed the ++ operator because of double evaluation. We also saw how it failed type checking. In C++, inline functions combined with templates solve both issues without losing performance. With optimizations enabled, the compiler generates identical machine code for the template function as it does for the macro. Basically, it inlines the logic, meaning the function call is replaced by the actual code. So the critical difference is safety. The template evaluates the A and B parameters once before the logic executes. This ensures that expressions like this work correctly without side effects, maintaining the same performance as a macro. One of the strongest holds the preprocessor had on C++ was conditional compilation, using #ifdef. We often use this to disable code segments, such as debug logging in a release build. When debug mode is undefined, the preprocessor excludes this block entirely. As a result, the compiler does not validate the code inside. If you introduce a syntax error or rename a variable inside this block, your release build will still succeed because that code effectively doesn't exist to the compiler. You won't discover the broken code until you specifically try to build the debug configuration later. C++17 introduced if constexpr, which allows us to perform compile time branching within the language itself. In this version, isDebug mode would be a constexpr boolean. The compiler parses the block even if isDebug mode is false. It checks the syntax, then it resolves the symbols. Then, during the optimization phase, it sees that the condition is permanently false and deletes the code from the binary. You get the same runtime performance as the macro with zero cost. But you also get the safety of the compiler checking your code every time you build. So if constexpr templates and modules are replacing everything, then is the preprocessor dead? No, there are still a few specific domains where macros remain the only viable tool. First, code generation and boilerplate reduction. As we saw with X macros, there is no standard C++ feature that allows you to iterate over a list of tokens and generate new tokens like enums and strings simultaneously. Until C++ gets standard reflection support, X macros are the best way to handle large tables of data that need synchronization. And while C++20 introduced std source location, many codebases are stuck on older standards. If you need to log exactly which line of code triggered an error, macros like _line and file are still the standard mechanism. You cannot write a function that knows where it was called from without these macros or the new source location features. You cannot use if constexpr to check if a header file exists. If you are writing cross-platform code that needs to include a specific header on Windows and some other header on Linux, you must use ifdef. The preprocessor runs before the compiler, so it can prevent the compiler from seeing headers that don't exist on the current operating system. Our goal as a C++ developer should be to use the compiler whenever possible, and the preprocessor only when necessary. When you do use the preprocessor, be careful. Use all caps for names, parenthesize your arguments, and keep the logic simple. So the ultimate goal of modern C++ is to stop using macros entirely. To see how modules finally solve the header guard problem or how concepts replace complex template macros, you need to understand the modern standard. Click here to watch my full breakdown of C++20, the essential upgrade for every C++ developer.